Rahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Azhar bin Aidil. So for the introduction, this assignment focus on understanding and analyzing control system. In task 1, a vehicle suspension system is modeled and simulated to study how it responds to disturbance in open and closed loop setups. Task 2, use the Rhodes-Lewis method to check system stability, finding gain range for stability, and using MATLAB to confirm the results. The assignment combines theory, simulations, and practical problem solving to explore control system basics. So for the question in task 1, we will be given the figure 1, which is about suspension system. So the question A for the task 1, draw the schematic diagram of the suspension system. So how to draw it? We have MV mesh block, we have KS spring, we have CS damper, we have MW mesh block, and we have KT spring. After that, we have XT as the rod. So we just convert the figure 1 suspension system to the schematic diagram of the suspension system. So in question B, write the sum of the force acting on each mass in the form of differential equation. In table 1, we will be given the parameter and the value of parameter. So how we do the differential equation? Firstly, we must add the MV plus CS plus KS, which is attach the MV mesh block. After that, we minus CS plus KS equal to 0, which is the equation is attached with MW mesh block. So that is the full equation 1. For the equation 2, we have MW plus CS plus KS and plus KT, which is the equation is attached with MW mesh block. And then we minus CS plus KS, which is the equation is attached with MV mesh block. After that, we minus the KTXT, which is the KTXT is attached with ground. After that, we bring the KTXT to the right. It is because the KTXT is different variable. And then for the equation 1 and equation 2, we just factorize the equation, and then to make a third equation, we must to add YW as a subject, and then we get the first equation to the differential equation. After that, we got the after we got the differential equation, we just substitute the third equation into the second equation. So after that, finally we get the full differential equation. So after this, my friend will insert the value of parameter in this fully differential equation.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Iqbal Haziq bin Azli. So I will continue question for task 1, which is task 1C, that assign us to obtain the transfer function YV divided by XS. So as we can see at the figure below, we change from the previous equation into the transfer function equation, which is output divided by input. So after that, we convert from the equation from the differential equation into the frequency domain. Then we substitute the value in table 1 into the equation, and after that we solve the equation until it gets the final value of transfer function, which is 300 million S plus 1840 million divided by 7500 S power of 4 minus 3,862,500 S power of 3 plus 43,690,000 S power of 2 plus 300 million S plus 1,840 million. And for the next question, which is task 1D, we assign to draw open loop block diagram. So at the left side, we can see that the block diagram we designed in the MATLAB by apply the transformation value into the transformation in software. So after that, at the right side we get the output response, which is the graph showed that the graph is in stable condition because it has a final value. And for the next question, which is task 1E, we assign to draw closed loop block diagram. So the block diagram is quite same like the previous block diagram, which is open loop. Just we add summing point and a feedback to make it closed loop block diagram. So after that, at the right side we can see the output response for the diagram. The graph shows that the graph is in stable condition because it has the final value. And for the next question, which is task 1E, we assign to draw closed loop block diagram. So the block diagram is quite same like the previous block diagram, which is open loop. Just we add summing point and a feedback to make it closed loop block diagram. So after that, at the right side we can see the output response for the diagram. The graph shows that the graph is in stable condition because it has the final value. Okay, so we continue for task 1E also. The task 1E assign us to compute the percentage of overshoot, peak time, response and rest time. So at the table below, we have found all the value, which is for peak value VP. We get the value of 0.680. For the peak time TP, we get a value of 0.237 second. For the final value V final, we get the value of 0.500. For the settling time TS, we got the value of 2.269 second. Then rest time TR, we got the value of 0.097 second. For the percentage overshoot %OS, we get the value of 36%. For the steady state error ESS, we get the value of 0.500. So I will pass the explanation of task 2 to my friend.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Hazal Saif bin Azman. Number matrix B11231053. Today I'm going to present task 2, which is the feedback control system. In task 2, we are assigned to using a root wave iteration to find range of K, which is stable, unstable or marginally stable. As you can see in the diagram, we are given a value of RS, ES, transfer function and CS. Question A, we are assigned to find the range of of k that will cause the system to be stable and unstable. As you can see in this slide, we are using C over S equation, which is the general equation for CS over RS is GS over 1 plus GS multiplied by HS. From the equation, we need to do the denominator times by 1 to get the numerator and denominator in the same value. Then we can cancel the equation. After that, we get the result k over s power of 4 plus 6s power of 3 plus 8s power of 2 plus s power of 3 plus 6s power of 2 plus 8s plus k, and we can simplify equal to k over s power of 4 plus 7s power of 3 plus 14s power of 2 plus 8s plus k. Okay, for value S2, we know the formula is CB minus AD over C. Then for value S2, we are going to multiply value 7 by 7 and 14 minus 1 times by 8 over 7. Then we got the value 12.85. We are continue the step until we get the value on the S power of 0, which is k. The next step, we are going to determine the marginally stable value, which is value of k. Then if we look into the equation or the row table, we are going to use the value 102.8 minus 7k over 12.85 is greater than 0 because the value is positive. Then we need to solve the equation by bring the 12.85 to the right side, and we got 7k greater than negative 102.8. Then we move the value of 7k, left the k on the left side. Then we got the last value is k is smaller than 14.69, which is k is the value 14.69 is the value of marginally stable. For stable value, k is greater than 0 and k is less than 14.69. For unstable is k over 14.69.
For this part C at task 2, I will explain how to find the actual location of the closed loop poles when the system is marginally stable. As you can see, there is 4 value of poles: P1, P2, P3 and P4. Before we get these 4 poles, we find that by using a calculator, and the name is polynomial equation. After we get that 4 poles, we can do a plot graph. For the graph, the x-axis is represent the real part of the poles, and the y-axis is represent the imaginary part of poles. The points are plotted based on the real and imaginary component at the poles. After we plot all the points or poles, we can confirm that the system is marginally stable because some poles P1 and P2 are on or near the imaginary axis. So basically, the graph is visually indicates the pole's location, and it also helps to assess the system visibility or stability. So for this part and part D, by using a MATLAB, we need to verify the value of k that cause the system in the stable and marginally stable or unstable condition. As we can see, this is the block diagram that we put it on the MATLAB. So for this part D, we need to use a MATLAB to verify the value of k that cause the system is stable, marginally stable or unstable. So after we input the value of gain that we obtain by using the Rhodes table method into the simulation in MATLAB. This is the output for all the condition. For the marginally stable, we found out that the value of k is equal to 14.69, and the stable condition is greater than 0 and below than 14.69, and the unstable condition is k is over or bigger than 14.69. So basically, this assignment is focused on control system through two main tasks. First is vehicle suspension, dynamics and stability analysis of unity feedback system. In this task 1, the suspension system was modeled mathematically and its transfer functions was derived. Simulations in MATLAB shows the closed loop system that improve response metrics like settling time and steady state error, demonstrating the benefits of feedback control. Next one is task 2. The Ropes-Hurwitz method was used to analyze stability and identify the gain range for stability. K is more than 0 and less than 14.69, and the threshold or marginal stability is K is equal to 14.69. MATLAB is verified these findings, showing how the theoretical and computation tools work together to better understand system behavior.
Lastly, before we end our video, for the conclusion, the assignment successfully demonstrated the application of control system fundamental to model, analyze and evaluate dynamic system. The mathematical modeling and simulation of the vehicle suspension system provided valuable insight into the role of feedback in improving system performance. Additionally, the stability analysis using the Ropes iteration and MATLAB validation highlighted the critical relationship between system gain and stability, and overall the task reinforced the theoretical concept while enhancing practical skills in system modeling, analysis and simulation. This comprehensive approach underscores the significance of control system in engineering application and their potential for optimizing dynamic system performance. That's all from us. Thank you.